New data and analysis have shown that Pluto is not a static relic. It is active, evolving, and filled with mysteries that challenge our understanding of planetary science. At the center of this transformation is its most striking feature, the Vassala heart-shaped region known as Sputnik Planitia. At first glance, it appears to be a smooth, frozen plain made of nitrogen ice. But this is no ordinary landscape. It is immense, so massive, in fact, that it affects Pluto's balance, subtly shifting its orientation in space. It's as if weight has been redistributed across the dwarf planet's surface. Beneath this Vassala icy expanse, scientists suspect something even more extraordinary, a subsurface ocean. Hidden under kilometers of ice, there may be a Vassala reservoir of liquid water, kept from freezing by heat generated deep within Pluto's interior. This heat likely comes from the slow decay of radioactive elements in its rocky core. Even at such a staggering distance from the Sun, this internal warmth could be enough to maintain pockets of liquid beneath the surface. If that ocean exists, it changes everything. On Earth, liquid water is one of the key ingredients for life. Wherever we find it, whether in deep ocean vents or buried beneath Antarctic ice, life has a way of appearing. If similar conditions exist beneath Pluto's frozen crust, then the possibility of life, however small, cannot be ignored. There are other signs that Pluto is not geologically dead. Its surface is marked by Vassala fractures, ridges, and fault lines, suggesting tectonic activity. These features indicate that Pluto's interior may still be evolving, slowly reshaping the crust from below. This is not what we would expect from a world that has been frozen solid for billions of years. Pluto's relationship with its largest moon, Charon, adds another layer of complexity. Unlike most planet-moon systems, Pluto and Charon orbit a shared center of gravity located between them, effectively forming a binary system. This gravitational interaction generates tidal forces that may flex Pluto's interior, producing additional heat. That constant stretching and relaxing could help sustain the suspected subsurface ocean, preventing it from freezing completely. This raises one of the most fascinating possibilities of all. If there is a liquid ocean beneath Pluto's surface, could it be alive? Some scientists speculate that microbial life might exist in such extreme conditions, adapted to darkness, cold, and immense pressure. These hypothetical organisms would be completely unlike life on Earth's surface, evolving in isolation beneath thick layers of ice. Discovering such life would fundamentally change how we understand biology and where life can exist. At the same time, not all the clues are easy to interpret. Observations have revealed unusual thermal patterns and chemical signatures on Pluto's surface. Some of these may be the result of geological activity, while others could be driven by complex chemical reactions. For now, their true nature remains uncertain, and that uncertainty is part of what makes Pluto so compelling. Pluto's origin also plays a role in its story. It likely formed during the chaotic early days of the solar system, built from countless collisions. These impacts could have generated enough heat to partially melt its interior, setting the stage for long-term internal activity. Over billions of years, that heat, combined with radioactive decay, may have kept parts of Pluto active, even as its surface remained frozen. Despite its distance, Pluto even has an atmosphere. It is thin and composed mostly of nitrogen, with traces of methane and carbon monoxide. Under faint sunlight, these gases react to form a reddish haze made of complex organic molecules known as tholins. These compounds are especially intriguing because they are considered building blocks of prebiotic chemistry, the kind that can eventually lead to life. Charon contributes to this system in surprising ways as well. Its surface shows Vassala canyons and fractures, signs of its own geological past. At its poles, reddish may have formed from gases escaping Pluto, drifting across space, and freezing onto Charon's surface. This exchange of material suggests that Pluto and Charon are not just gravitationally linked, but chemically connected. What makes Pluto even more remarkable is its location in the Kuiper Belt, a distant region filled with icy remnants from the Solar System's formation. Most objects there appear inactive and unchanged. Pluto, however, stands apart. It has moving glaciers, a shifting atmosphere, and signs of internal processes. It is active in a place where activity was never expected. And that leads to a bigger question. If Pluto can sustain this level of complexity, how many other distant worlds might be hiding similar secrets? Could subsurface oceans be common in the outer solar system? Could life exist in places we once thought impossible? Future missions may one day return to Pluto, orbit it, and study it in far greater detail. Perhaps they will probe its atmosphere or even attempt to peer beneath its icy shell. Each new discovery has the potential to reshape our understanding of how planets evolve and where life might arise. Pluto is no longer just a distant of ice and rock. It is a world of motion, chemistry, and possibility. It challenges old assumptions and opens new questions. And perhaps most importantly, it reminds us that even in the coldest, darkest corners of our solar system, there is still so much left to discover. The question is no longer whether Pluto matters. The question is what secrets it still holds beneath its frozen surface, and what those secrets might reveal about the universe itself.